a snippet of what the short course is going to be about if I get the opportunity to present a short course to the OPA. So the first thing I'll talk about is a case study in determining optimal artificial lift implementation in the Midland Basin. This was an SPE paper for those of you who want to have more information about the production optimization paper. So I'm just going to go ahead and give you the presentation and then go ahead and read the paper for more details. The objective of this study was to evaluate various artificial lift strategies based on production data analysis and general operations. This was also to generate a workflow to optimize artificial lift strategy by integrating reservoir modeling with vertical flowing pressure modeling. And candidate wells are located, for those of you who are not familiar, this is in a gassy region in the southern Midland Basin called the Wolfcamp D Formation. And then there's the northern Midland Basin Lower Sprayberry Formation. Some of the takeaways that I'll talk about in this presentation is that the ESPs had the highest downtime and the gas lift had the lowest downtime, and that's including compressor downtime. The workflow can also help operators improve economics, particularly NPV for Wolfcamp D wells, by recommending a gas lift installation at the beginning of production and then switching to rod pump. And then the workflow can also help operators improve NPV by recommending a combination of ESP to rod pump conversion in the Lower Sprayberry Formation. And you'll notice that the GORs are going to be a little bit different. The gassier formation is the Wolfcamp D formation, and then the ESP in the Lower Sprayberry is a less gassy formation with the GOR of less than 2,000 scuffs per barrel. This is an overview of where the candidate wells are located. For example, this one is located in the southern Midland Basin. So all the orange that you see are acreage of university lands. And then you'll see the snapshot of where we're talking about in terms of Permian Basin. So this is the Midland Basin, the southern Midland Basin in particular, and these are all the reservoir parameters that we're talking about. This is in Upton County. Reservoir pressure is 5,900 psi. It's a high GOR. Initial GLR is relatively high. And the artificial lift that the operator used for this particular well was it was on a natural flow for a year, and then it was converted to a gas lift. The second candidate I'll talk about is the Lower Sprayberry well. This is located in Andrews County. The reservoir pressure is 4,350. It's a low GOR and GLR well. And the artificial lift strategy that was used is high rate and low rate ESP in combination. So the first thing I'll talk about in the workflow is that you'll have to look at artificial lift optimization. And this is for new wells. You collect data and you do some QA/QC. You build well performance models. So everyone pay attention to the left side of the plot. You calibrate numerical simulation models or an RTA-based analytical model or type curve. So there are 3 different ways that you can, depending on the level of complexity and how much data you have, to develop your well performance models. Then you forecast the productivity index over time. You build wellbore models with different artificial lifts. And then you build wellbore models with different artificial lifts. You forecast rates and flowing bottom hole pressures of different artificial lifts over time. Then you assess the downtime, cost, and operational limits of different artificial lifts. And then finally, you determine the different scenarios of single artificial lift or combined artificial lift for wells in a lifetime, perform economic analysis for all scenarios, and then recommend the optimal artificial lift strategy. The slide that I also want to show are the difference between conventional and unconventional reservoirs. In conventional reservoirs, you'll notice that the reservoir pressure dramatically changes whenever you have whatever different time steps. But the difference here is that the reservoir pressure doesn't change as quickly compared to the IPR curve that you end up generating of absolute open potential flow. So you'll notice that the IPR curves change a little bit different in unconventional reservoirs than you do in conventional reservoirs. And we combine this with VLP curves, which are the outflow curves, the lines with the dots. And we try to figure out at the specific VLP curve in the intersection, when is it time to convert from one artificial lift to another? So we did some downtime analysis, or I did some downtime analysis, and red represents the gas lift, green represents rod pump, and blue represents ESP. The biggest takeaway is that ESP had the largest range of uncertainty and then the highest downtime percentage, whereas gas lift had the most narrow uncertainty and the lowest downtime percentage. These are the ranges of scenarios that were used in this analysis or in this workflow. And you can use this workflow in a variety of liquid rates and flowing bottom hole pressures, but this is just an example of the workflow based on the data that we had. So the natural flow, you'll notice where it was actually being flowed from, whether it was tubing annulus or tubing flow, or how long it was on natural flow. And then a high rate ESP, there's a liquid rate at which you start converting to a high rate ESP. Then you have a middle rate ESP, a low rate ESP, a gas lift, and then a rod pump. And then you'll notice some pressures below where you have minimum flowing bottom hole pressure at ESPs around 600, gas lift, the minimum flowing bottom hole pressure was 500, and rod pump is 300 PSI. It's not always in this particular order. What I will say is that it really depends on the data that you have to know at which minimum flowing bottom hole pressure you can have before converting from one artificial lift to another. And we also incorporated average downtime, which was shown in the downtime analysis in the previous slide. Case 8 was what was used from the operator in that it was on natural flow for about a year, and then at 400 barrels of liquid per day, it was on a gas lift. Another thing to take into account are the pressure profiles, are the rate and pressure profiles. Blue represents liquid rate, orange represents your flowing bottom hole pressure, and gray represents your reservoir pressure. You'll notice that at different times, at different minimum points, whether if it's liquid rate or flowing bottom hole pressure, you convert from one artificial lift to another. So based on the simulation, it's suggested to switch to a gas lift on day 4, and then switch to a rod pump on day 234, so 8 months into the program. These are cumulative curves that are based off of the artificial lift strategies. You'll notice that the case with the minimum flowing bottom hole pressure gives a higher cumulative oil production. And then you'll also notice that at case 8, which is that brown line shown over here, you'll notice that the operator did not have maximum cumulative production when it was on a natural flow for about a year. Now, for the Lower Sprayberry well, it was converted to a high rate ESP at 3,500 barrels of liquid per day, and then a mid rate ESP at 500 barrels of liquid per day, if you look at case 8 from below. But this is using the same types of ranges of scenarios that you can use in order to compare what is the optimal artificial lift from this workflow. You'll notice over here that Lower Sprayberry results were a little bit different in that you switch to an ESP on day 2. You immediately turn on the well with an ESP on day 2, and then you switch to a low rate ESP on day 215, and then you switch to a rod pump 3 years in the program. We also thought about gas lift, if gas lift was a possible option. However, based on the decline of these wells and the pressure and production, there was an immediate switch to a rod pump directly. And this is assuming that the gas lift injection was 500 MCF per day. Therefore, a gas lift of 500 MCF per day was not efficient according to this workflow. So these are the ranges of cum curves, and then you'll notice that from natural flow to gas lift, there was a lower cum because of a natural flow to gas lift, but every other case that had an ESP was relatively close to each other. These were the economic values that were used in the case. You can use your own economic values, and just notice that take these economic values with a grain of salt because these were values from 2017. Using the economics, you'll notice that the orange represents the NPV for each artificial lift scenario, and the blue represents the EUR for each artificial lift scenario. You'll notice that the optimal artificial lift is actually the natural flow to gas lift to rod pump in your Wolfcamp D formation because it had the highest NPV. And then in the Lower Sprayberry, you'll also notice that the natural flow to gas lift the natural flow to high rate ESP to low rate ESP to rod pump when you're in the operating range for these particular wells had the highest NPV as well. Then you'll have the gas lift sensitivity. We asked the question that what was the optimal gas lift injection rate in order to get the same competitive cum as you would do with an ESP. The highest EUR NPV injection rate was at 2 million, and current operators' gas injection rates are not that high. So therefore, gas injection in the lower Sprayberry was not going to be efficient for a low pressure, high GLR, high liquid producing well. So the conclusions of this paper was that the workflow can be used to optimize artificial lift strategies in the Midland Basin. And you'll see what the Wolfcamp D and the Lower Sprayberry formations optimal artificial lift was. And then integrating calibrated numerical models enabled forecasting in the long term with well performance and selecting artificial lift. And then optimal gas injection and port size sensitivity analysis should be taken into consideration. Now I'm going to go to another part of the presentation in terms of, I'm going to now talk about another part of the presentation, which is going to talk about lateral lengths. So this is SPE 187502, which is production optimization in the Midland Basin through lateral length multi-phase flow simulation. So this is another snippet of what the short course can talk about and covering some of the cases, the case studies in the Permian Basin. I want to start off with this plot where you're looking at oil EUR versus lateral length, and you'll notice that it's all over the place. We also color-coded this based on toe-up, toe-down trajectories, and we also shaped this based on if it's Lower Sprayberry or a Wolfcamp B well, which is another formation in this particularly, and it's in this particular formation. You'll notice that it's all over the place, but the higher the lateral lengths, the larger the EUR. And the question we're trying to ask is, can we use simulation in order to answer the question of how much oil we can get out of the ground? So this is some rates that you'll notice to, or your notice of ratios based on lateral length and EUR ratios, and they're all over the place too. This is assuming that a reference lateral length is at 7,500 feet and the EUR ratio is 1:1. But you'll notice that as you double in lateral length, not all the time you're going to get a 1:1 ratio of production uplift. So that's the main takeaway from this slide in the Lower Sprayberry and the Wolfcamp B on the left side and in the right side of this slide. So the objectives of the study was to determine optimal lateral lengths and trajectories in the Midland Basin by studying the impact of lateral length and trajectory on well production performance. We delivered a workflow that couples reservoir simulation and wellbore simulation, and I wanted to study the impact on cumulative production by lateral length and trajectories. A Lower Sprayberry well, which is low GLR, and then a high GLR well, which is a Wolfcamp B formation. You'll notice that this is a similar workflow that was shown in the artificial lift. I want everyone to pay attention to the left side of the workflow, where you match production with the original wellbore design. You evaluate production outcomes with different time steps with each perfect trajectory, and you keep the same productivity per unit length. Then you evaluate the wellbore contributions for each trajectory. And if there are significant differences, then you perform an economic analysis of different wellbore constructions. And then you recommend an optimal wellbore construction with respect to reservoir performance. So the left side of this workflow is very similar to the artificial lift optimization case study. The right side now talks about if we were to look at different trajectories, what is going to be the optimal EUR by keeping PI constant or productivity index constant. So some of the modeling results, the toe-up trajectory had the best oil and liquid production. The more undulations you have, the more liquid holdup and the less likely you're going to have a 1:1 ratio. And then the gassier wells you have, the less likely you'll have a 1:1 ratio. So the Lower Sprayberry had EUR ratios of about 2, and the Wolfcamp B had an EUR ratio about 1.6 when doubling the lateral length. And this is a plot just to show that in the Lower Sprayberry, if you were to have a normalized lateral length, you have a 1-to-1 ratio of production uplift, whereas in the Wolfcamp B, the production uplift is not 1-to-1. This is the same view of looking at the well candidate and their respective reservoir pressure and in parameters. This is a Lower Sprayberry in Andrews County. And then this is another well in Wolfcamp B well in Erie County with the respective reservoir pressure and parameters. This is a snapshot of some of the reservoir modeling that we did, that we calibrated numerical models and the simulation model, and this shows the history match that was also done. It was a good history match of matching oil, water, and gas and pressure. The one thing to pay attention is the productivity in unconventional reservoirs. So this is a takeaway that I want everyone to get in the class, is that liquid PI and production days, the productivity index is going to change throughout the life of the well compared to conventional reservoirs. So that is something to pay attention to in unconventional reservoirs. Now, these are the trajectories that were used. You have the original trajectory where it was a little bit of a toe up, but there was a lot of undulations. Then you have a flat trajectory, a toe up, toe down, and an undulated trajectory. We use the simulator Olga. So for those of you in offshore applications, you've used Olga. This is a wellbore flow simulation example at day 30. You'll notice that there's a wellbore trajectory and the flowing bottom hole pressure changes over time. The units of each time step are unit PI, GOR, and water cut, reservoir pressure, and the pressure boundary conditions, which is at the top of the heel. The green now represents the liquid holdup that you get at different parts of the trajectory. You notice that when there are dips, there's actually a more liquid holdup. And then at a toe up configuration, you'll notice that the liquid holdup is a little bit different too. And then you'll also notice that the flowing bottom hole pressure is different as you go from toe to heel. Now, these are the liquid productions that I want everyone to pay attention to at early time for the Lower Sprayberry. These are calculated liquid productions at different trajectories, and you'll notice that the production ratios between longer and shorter lateral lengths are consistent for the production time of accumulation. So the right table represents a 1.5 mile. The left table represents a 1.5 mile. The right table represents a 3-miler. These are the trajectories at different lateral lengths and at different liquid holdups. You'll notice that the undulation at the lowest cumulative production, and the longer the lateral length and more liquid production that you have, or the more undulations that you have, then the more difference that you have between the undulations and then the perfect trajectories. This goes for the Lower Sprayberry as well, after 30 years. So this is also calculating the EUR. Now, these are the EUR results for the Lower Sprayberry, in that you'll notice that toe up and flat wells have promising incremental recoveries in this case. You'll notice that the percent differences are the ones that you want to pay attention to compared to the flat case, which was the reference case or the perfect trajectory case. And you'll notice that the toe down case has a detriment to production compared to toe up. And these are EUR ratios. You'll notice that the EUR ratio, the production uplift is close to 1-to-1. You'll notice that it's between 1.8 all the way to 1.98. And these are the Wolfcamp B EUR ratios as well. You'll notice that these are a little bit lower in production uplift, where vertical undulations are between 1.6, whereas the highest production uplift you're going to get is a toe up at a 1.85 or a flat at a 1.87. So the conclusions of this work is that the workflow allows rigorous modeling to determine pressure decline along the lateral, wellbore contributions, and then undulation effects on production rate and EUR. The impact of trajectories on production is that the toe-up well trajectory consistently results in oil and liquid production for high and low GLR formations. And then the vertical undulated wellbore may have the worst impact on recovery. And this workflow helps determine what the EUR uplifts are going to be when you double the lateral length. You'll notice that the lower Sprayberry is from 1.8 to 1.98. Wolfcamp B is from 1.6 to 1.7. So that's a snippet of learning about lateral lengths in the production optimization space. Now I'm going to talk a little bit about underperforming wells in this presentation. So this is another case study of evaluating underperforming wells on Permian Basin university lands. The objectives of the study is to understand current well performance on university lands horizontal unconventionals. And then you have the Midland Basin and the Delaware Basin. And this was meant to develop a workflow to determine future steps on improving existing wells and upcoming acreage development. So this is the same workflow shown on the previous slides, but you'll notice that the content is a little bit different. You collect the data, you identify the highest completion intensities, which is tight cluster spacing and large sand fluid volumes pumped per foot. Then you identify the P50 daily production for selected wells to generate type curve EURs. You compare the normalized EURs for all wells with completion intensity type curves normalized EURs. Then wells below 50% of the type curve are classified as underperformers. Then you identify the root cause of underperformance, which is completion intensity, artificial lift, geology, or fluid properties. Then you identify common traits of underperforming wells with respect to each formation and bench. Then you identify re-stimulation candidates or artificial lift optimization based on root cause and well economics. These are the areas that were located in university lands, areas 2, 3, and 4. 2 is the Delaware Basin, 3 is the Northern Midland Basin, and 4 is the Southern Midland Basin. You'll notice that in area 4, it's a geologically diverse area based on GORs, where the western part has a lower GOR and the eastern part has higher GORs. The takeaways is that at least 20% of university land Wolfcamp wells at all intervals were underperforming, which is 50% of the wells evaluated in the study. The root cause is low completion intensities, even with recently completed wells. Southern Midland Basin's root cause is geology, poor reservoir quality, and high gas migration eastward. Improvement opportunities for Area 4 Middle and East is continued gas lift optimization strategies. But the other opportunity is refrac as well in the other areas. So this is a plot of well identification where you'll look at the type wells, lateral lengths, proppant, fluid, and cluster spacing. And these are separated by each area. Then you have the different formation and blocks, university land blocks that discriminate of the university land formation and in the block. And then you'll look at the total wells with daily production data, total underperforming wells of interest, and then total by area that are underperforming. So based on this number, 53% of the wells evaluated, 20% of all university land horizontals are underperforming. These are single well economics. Don't pay too much attention to the numbers, rather pay attention to more of the single well, or pay more attention to the single well economics workflow. And then based on the economics, we'll notice that 18% of all university lands are critical wells or do not have a positive initial rate of return or internal rate of return. So we looked at the first root cause, which is completions, and then we looked at all the formations at different blocks in Area 4 in different formations. And you'll notice that there's a wide range of fluid per foot and cluster spacing. And these are older vintage wells. Then we also looked at total EUR versus RTA results, and you'll notice that the underperforming wells have not only have low EURs, but also low A square root of K, so low completion effectiveness. This is a total EUR versus average pump rate, so you'll notice that the higher the pump rate, the higher the EUR in different formations. And then the root cause investigation, we also looked at geology in Area 2. But the biggest takeaway that I want you to get from this slide is that geology it was inconclusive, faulted portions deterred production. And underperformance most likely came from vintage completion techniques, where you had stage spacing up to 300 feet, cluster spacings up to 200 feet, and then you had less than 1,000 feet of sand and 20 barrels of fluid pumped. Then we looked at root cause of investigation or geology in Area 3, where there's virtually no underperforming or uneconomic wells. You have high oil saturations, favorable TOC and maturity for Lower Sprayberry to be favorable landing zone. And then you have locations with the highest completion intensities, and any indication of underperformance comes from understimulation. Then you have Area 4 West and Area 4 Middle and East. Area 4 West has relatively oil-rich geology, where Area 4 in the middle and the east has poor reservoir quality and gas migration eastward. So geology is a root cause. And then we also looked at fluid properties. It could be a sensitive parameter, or artificial lift, which is least likely a sensitive parameter. Then we looked at candidate selections for refracts as well. So candidate selection for refracts are between 200 to 500 foot cluster spacing, low sand and fluid pumped, and RTA results had low A square root of K. We found 1 to 2 wells in areas 2 to 3, but it was questionable incremental economics, and Area 4 may not be worthwhile despite significant understimulation. As far as artificial lift goes, you've seen these slides in the previous presentations, but the short course will go more into detail as far as how artificial lift does play a role in underperformance. So therefore, the conclusions of this study is that the workflow effectively narrows down critical wells from the completions-based type well with respect to different unconventional formations. The root cause is low completion intensities in areas 2 and 3, and then Area 4 is completion and geology. Now we're going to talk about, as the last topic, of gas to oil ratio considerations. So what is the importance of GOR? The importance of GOR is to determine what artificial lift to install, gas takeaway facilities, fluid properties in a reservoir, and then what can GORs tell us? So this is a case study. And some documented trends. Early GOR in unconventional reservoirs is that early GOR is constant at initial solution GOR, where flowing bottom hole pressure is above bubble point. And then GOR rises when flowing bottom hole pressure goes below bubble point. Transient GOR plateaus, characteristic of linear flow. So that's pushed me to talk about the physical mechanisms of GOR. Thermodynamic phase behavior and fluid and rock interaction are still not well understood. Contributors to nonlinearity are PVT property suppression, pressure-dependent permeability and compaction, and critical gas saturation changes. GOR is not only a function of flowing bottom hole pressure, but also a fracture geometry, gas and oil PVT properties, and gas-oil relative permeability curves. Suppressed bubble points and flat GOR trends at early time are confined and mid-confined nanopores, nanopore proximity on fluid and rock and transport properties, and then capillary pressure changes. The expected trends is that GOR provides an inverse relationship to the recovery factor in liquids-rich shales reservoirs. The recovery factor of bubble point is sensitive to GOR and could range between 3 to 5.5%. And modified hyperbolic models are the appropriate decline curve analysis models for these GOR trends in the Permian Basin. So actual trends is that increasing GORs due to depletion below the bubble point than expected are indicative of sharper oil production decline than originally forecasted and actual GOR trends in unconventional plays. An example is that in Sharma's study is that there's a clear impact on terminal declines in the Middle Bakken. And this is an Enverus study in 2019. This is a GOR trend per well versus cumulative oil. You'll notice that when you reach bubble point, you reach that inflection point, which is in the circle on the left side of the left plot. And then you'll notice that if you group wells, the average GOR gets higher at different vintages. Older wells could have had higher drawdown to reach bubble point at earlier times. So that's another takeaway. So additional findings of this example one is that wells with higher GORs came from portions of the studied area with high solution GORs. Increasing GORs are a function of geothermal gradient, TOC, maturity, operational strategy, and completion strategies. So you've already seen this with the Southern Midland Basin and Wolfcamp B. But the PVT properties I would like for you to take away is that you collect separator samples with low drawdowns, and it's best to simulate in situ conditions. Combine advanced PVT modeling with single well reservoir simulation to match the production performance using fluid initialization parameters such as key history matching variables. Black oil reservoir simulation can be used, but PVT table should be generated from an equation of state. And then you have to understand a well stream's composition over time. Gas can easily break out a solution, normalize for changing separator conditions. Separators could also change considerably over time. And then knowing a well stream composition over time could help normalize the GOR to get a better understanding of these trends. So there's also another study that's been done with 10,000 Permian wells, 12,000 Bakken wells, and 10,000 Eagle Ford wells. You'll notice that the GOR is very different for each one of these, where the GOR in the Eagle Ford and the Permian is at 2,000 and increases to 3,000 to 4,000. This is initial GOR. And the Bakken's GOR averages 1,000 SCF per barrel and remains relatively constant. So there's consistent pore size changes within the source rock to maintain undersaturation. Then you'll look at reservoir simulation efforts where RTA is appropriate to choose as initial values for matrix and enhanced zones. Confined and mid-confined phase behavior effects are from nanopore, mesopore, and macropore diameters, giving a suppressed bubble point trend. There's some triple porosity and SRV models we'll go into the course, and they'll represent different pore size distributions of flatter GORs for a longer time period. This is the inclusion of rock compaction to represent the physics behind observed GOR trends. And then I go more into detail of common reservoir models, relative permeability measurements, and pore size distribution effects. But the one thing to take into account are the conclusions of the study, is that the bubble point suppression is observed. It's caused by capillary pressure effects in mid-confined nanopores. But the acceleration to deplete the reservoir below bubble point is also observed through aggressive drawdown strategies. And then here are a number of factors that affect GOR trends: flowing bottom hole pressure, PVT property suppression, pressure-dependent permeability, changes of critical gas saturation, fracture geometry, pore size distributions, and gas-oil relative permeability curves. So then, despite differences in GOR trends between unconventional and conventional reservoirs, the industry will continue to use modified hyperbolic because this still matches the empirical data well. Modeling techniques have to have varied pore size distribution, capillary pressure, and defined matrix and enhanced permeability zones to provide a comprehensive context on GOR. With the normal trends of GORs, drainage area and pore sizes ought to be taken into consideration. More drainage means that nanopores from the shale matrix will deplete, which will increase GORs. So that's everything that I wanted to discuss in this paper and in all the papers that I've presented. And I am open for questions. I wanted to leave plenty of time for questions. And I noticed that there's a number of people that have talked in the chat. So I'm going to see what this chat is from.
Thank you, engineer, for this fruitful session. Let's have a 5 minutes break until the attendees fill the feedback form that I will send in the chat box right now. And then after this 5 minutes, we will receive your questions in the chat and you may answer it, Engineer Yugashi.
Sounds good.
I've sent the feedback link in the chat box. Please, all the attendees, I want you to fill it, please. Okay, let's have that in this question. The first question from Marco, he is asking, early when you were talking about optimal lateral length, could you give us an insight of what is the potential benefit of horseshoe shape extra long laterals being drilled in the Permian?
Sure. Yeah, there's definitely been a conversation on horseshoe laterals, and I would say the jury is still out. There's definitely some drilling complications that can come with it. But as far as and completion complications that can come with it too. But as far as the uplift, it's probably cheaper. than drilling two wells of different lateral lengths or of the same lateral lengths that are next to each other. And the jury is still out in trying to figure out whether if you're going to get that one-to-one uplift. I think depending on how you draw down that well, I think it really does depend. So yeah, that's definitely a question that of interest for a lot of people in the Permian.
Thank you. Another question from Karim. How can you assess the potential of unconventional reservoirs? In other words, can we run MBEL, decline curve analysis, etc.?
You can definitely run decline curve analysis on different types of analogous wells. And then as far as material balance goes, you can using simulation. You can also use simulation to understand the potential of the reservoir.
Thank you. Another question. Um, Peace wants to know how does the GOR determines that the selection of a particular artificial lift method to be used in a well that has a low pressure due to production over the time?
That's a good question. The GOR really is a component of whether if the artificial lift is going to work or not efficiently. And usually gas lift wells are high GOR wells because you have gas down there to begin with as high pressure. ESPs, for example, have a lot of jewelry to where you can have the best gas separator, but gas locking could happen. With rod pump, gas locking could happen as well. So that's why with high GOR wells, having a gas lift is definitely one of the recommendations for artificial lift.
Thank you. I think this is the last question from Roger. How can we manage a weathered basement reservoir?
I don't know what a weathered basement reservoir is.
Can you clarify more, Engineer Roger?
Hmm.
I think we have missed a question before Roger. Someone was asking which software is used for numerical model.
Petrel.
Petrel, okay.
And Roger says reservoir is not continuous. So there are a lot of uncontinuous reservoirs in the Permian Basin. And you have to understand the extent of the geology. I don't know what a basement is alterated. I really don't know what that is. I would say that if it's an uncontinuous reservoir, you have to understand the sweet spots that you're going to drill or the sweet spots of that particular area of where you're going to develop in your acreage. So for an uncontinuous reservoir, you have to learn what the trade-offs are in terms of drilling into a particular spot. If you don't have an optimal spot, but you need to build up inventory, you can drill the well, but you can't expect much from it. So you try to drill the well as cheap as possible. Oh, if it's not a depositional environment. Okay. Usually it has to be in a depositional environment, the unconventional reservoir.
Okay,
Any
I
other? Mhm.
continue, Phil.
Oh, I was talking any other questions?
No, I think it's all for today. Thank you, Engineer Yugashi, for this informative session and fruitful webinar. And thanks to all attendees for attending, and see you in our next webinars. Thank you.
Thank you.
There is another question. Please, I want more explanation on how the completion of a well affects the well underperformance.
Sure. So the completion of a well affecting the underperformance is a completion is really the driver of how that well is going to perform. Proppant is going to keep those fractures open. Water is going to help transfer that proppant. So if it's a low stimulated well, like there's not enough sand that was pumped, there was not enough fluid that was pumped, there were probably not enough fractures that were created or propped. So that contributes to the well's underperformance.
Okay, thank you.
All right, thank you so much.